All right, so last time we were talking about this idea of potential energy. And this idea of potential energy is that we have this sort of energy savings account where we can take energy that is kinetic energy or maybe work or energy from another source. We can take this energy and put it into this savings account and use it a little bit later. And we use the idea of a soccer ball bouncing up and down. On its way up, we put energy into the savings account, increasing our potential energy. And on the way down, we have our energy savings account used up, turning that energy into kinetic energy. Now, I said that we get these potential energies depending on the forces that are involved, and when we have special types of forces, we get these energy savings accounts. But the question becomes, what forces give us an energy savings account and which ones don't? And this is a question that relies on this idea of conservative and non-conservative forces. So when we take a look at conservative forces are forces in which we get these energy savings account. We call it this because it conserves energy. So we want to know, is a force conservative or not? And that's actually one of our goals today. How can we tell if a force is conservative? And if a force is conservative, can we determine the potential energy from that conservative force? These are the questions we are seeking to answer today. So to begin with, we answer the question of what is a conservative force. And a conservative force is one in which we consider the work done through a closed path to equal zero. That is the definition of a conservative force. That if we have something moving in a closed path, that the work done on that object is zero if it is done by a conservative force. So what does that mean? And that means we imagine an object at point A. This object is going to move to point B, and it's going to take some path to get to point B. Just didn't mean to put W there. It'll move to point B. And once it's at point B, it will then decide to make a return trip, whatever that trip looks like, back to point A. So we have a closed path here. We end at A and we start at A. And if we take a look at this, we can figure out the work done from A to B, and that's going to equal some value. And it's going to equal a non-zero value specifically. So I'm going to say that this does not equal 0. We look at the return path and we say the work done from B to A. That is also going to be non-zero. And then finally, we ask the question, well, what is the total work done in this closed path? Well, the total work done is going to be the work done from A to B, and we're going to add to that the work done from B to A. And if the force is a conservative force, and only if the force is a conservative force, do we get that the work done is 0. If it is a non-conservative force, then it will have some value, and I'll show you an example of that shortly. So let's take the example of a box of some mass m. And this box of mass m is going to move from point A to point B. It's going to move from point A to point B, and then it's going to move from point B back to point A. This is again a closed path because we begin and end at the same place. During its path, it is going to have several forces acting on it. It's obviously going to have the weight acting on it, which is mg. We have the normal force acting on it. We have some sort of a push that I'll just label as F. And then we also have a friction force pulling it backwards. And really what I want to look at is this friction force. We're going to determine, is this friction force going to be a conservative force? So we look at this and we say, okay, well, the work done from A to B, that is going to equal the magnitude of our friction force, which in this case is going to be the coefficient of kinetic friction multiplied by mg. We multiply that by the displacement. So I'm just going to call that delta x. Delta x is whatever the distance is between A and B. Maybe it's 3 meters. I don't really care at this point. And then we multiply that by the cosine of the angle between our friction force and our displacement. Well, our friction force is to the left, the displacement is to the right as we move from A to B. So that's going to be 180 degrees. And when we take a look at this, we can say that 180 degrees, well, cosine of 180 degrees is always going to be negative. So we have negative mu of k, the coefficient of friction, mg delta x. And that gives us our first path. We also want the work done from B to A. And the work done from B to A is going to be, again, friction. We are only looking at the work done by the frictional force. We're trying to determine, is that friction force a conservative force? We move again at delta x. It's the same distance if we go from B to A as it is if we go from A to B. And then we multiply that by the cosine of the angle between them. And upon the return trip, the force is going to resist our motion, B backwards, and our displacement, delta x, and that is the kinetic friction force specifically. And the displacement delta x, well, that's going to be to the left, meaning we still have cosine of 180. So negative mu of k mg delta x. So if we want to know the total work done in this closed path, the total work done is going to be 2 times negative mu of k mg times delta x. And when we take all of these values, well, none of these values are going to be 0. So that means that this does not equal 0. And that tells us something. That tells us that friction is a non-conservative force. How do we know? Well, it didn't end up having 0 total work overall throughout its entire path. So there we have it. Friction is non-conservative. There is no potential energy, no savings account related to friction. And then you might ask the question, well, what kind of forces do give us a savings account? And one of the forces, and we've already seen this, is gravitational force. So what we'll do is we'll take a ball, right? Try and draw my soccer ball here. My poorly drawn soccer ball. We are going to take a soccer ball, move it up, let it come back down, starting at point A, going to point B, and returning. The work done to go from A to B, well, it's going to be the force, the mass of the ball times acceleration due to gravity, times the distance that is traveled, I'm just going to call that delta y, times the cosine of the angle between these. And as we move upwards, the force is downwards, the delta y is upwards. That's going to be cosine of 180 degrees. The work done here, negative mg delta y. Okay, well, what about the return trip? On the return trip, we look at the work done to go from B to A. And that's going to be mg delta y, again for the same reasons. And then we have cosine, and now we ask the question, what is the angle between them? And both of these are downwards. The ball moves in the displacement downwards. We have a force that is downwards, cosine of 0 degrees, which means that's going to be positive mg delta y. And you ask about the total work. Well, the total work here, when you add those together, ends up being 0, which means work done by gravity is a conservative force. So gravity is conservative. And what's interesting is this isn't just with this gravitational force as mg. This is true regardless of if we look at local gravity, weight is mg, or universal gravity, g/m over r squared. All right, so then the question is, do we meet our objectives, and how do we determine if a force is conservative? Well, we see, is the work done over a closed path equal to 0? Then how do we determine the potential energy from it? To determine the potential energy, we take this gravitational force, and we say that the potential energy is equal to the negative of the work done. Or rather, I should say the change in potential energy. And here that's easy, right? The work done by gravity, well, gravity does work if we move up or down. And if we move upwards, we would say that the work done is going to be, if we are moving upwards, we say negative mg times the height that we move upwards. In other words, that's just going to be mgh. So the change in potential energy as we move upwards is mgh. So how do we determine the work, or how do we determine the potential energy? The potential energy is given from the negative of the work. And we can see that for a few others. I'm going to review with you guys the case of a spring in the next video because that's going to be a little bit longer. It's going to involve a little bit of calculus. So we'll do the spring in a separate video. All right. So if you have any questions, let me know. Otherwise, I'll see you guys in the next video.